this particular x is as a explanatory variable. So this is a simple linear regression equation. So linear means it is understood that it will go generally straight line. So with the degree of 1, if nothing is there means it is understood that it has 1 here. If it is non-linear means it has higher degree. Quadratic equation y is equal to a plus bx plus cx square or dx cube, all those are quadratic, cubic or exponential or logistic or any of the form which doesn't follow the rules of the linearity. So we actually focusing on only linear equations. We are not at all going in the non-linear way. So only linear equation either in simple form or multiple form. Okay. So multiple linear regression equation generally looks like this. So here, as I said, this will be the independent variable. This is beta naught. Beta naught is a constant and we can call it as an intercept also. So beta 1, beta 2 up to beta n, all these are explanatory variables or dependent variables. So this is called as an error term. This error term we will learn very clearly later. So how these things can be explained is how these explanatory contributes to this dependent variable we need to understand. The error term is called as residual for the observations for the multiple regression model. So any regression model has to satisfy certain conditions or certain assumptions. When we actually see the multiple linear regression, it has to follow certain conditions. These are the conditions. The model won't be finished if we don't add this particular error term, and this error term has some kind of rules. This particular, the expectations of this error term should be 0. That means the mean of this expectation should be 0 and the variance should be constant, that is a square or sigma square I mean to say here, and the covariance between any pair of EI is it should be 0. This particular thing should not be equal. And then normally says this particular E, that is error term, should follow normal distribution with mean 0 and variance sigma square. And further, there if we want to say in this aspect, the entire thing of previous slides, I can just say normality of residuals of errors and equality of the variance of the errors. So these things should follow. And additionally, the model should not contain multicollinearity aspect and autocorrelation aspect. Out of these two, we will going to learn in detail about this multicollinearity and autocorrelation later. So I said about the error term. Error term is very, very important to understand to complete the model, because without error term, all the errors which generally comes in any aspect of the model, we won't, it will not get signified. Okay, we will see error term composition. So one thing is systematic component of y, the mean of y generally, that composes of b1 plus b2 plus x. This doesn't complete it until and unless this E get completes here. So this has to be added, that random error. Random and error component includes y minus the expectation of y. This expectation of y is generally b1 minus b2 of x. So we actually do some mathematical algebraic stuff here. So these two components forms together, this is expectation of y and this error components forms the model. Without why this error is so much important means I have made some following observations here. In statistical language, we call the error term is also a stochastic error term, which we generally present in regression equations. If you generally observe, many minor influences on y are omitted from the equations. For instance, because of the data are unavailable or some mismatching in the data, or there are so many external aspects. We divided the entire errors into two possibilities. One is assigning errors and chance causes. So assigning error can be controlled by human and chance causes cannot be controlled by human. All those things which generally go into the error aspect. So it is virtually impossible to avoid some sort of measurement error in at least one of the equation variables. So underlying theoretical equations might have different functional forms. That the one of the aspect of choosing for regression. For example, the underlying equation might be nonlinear in the variables for the regression. So all the attempts that we generalize to contain some sort of unpredictability or uncertainty or purely random variation. So here only one statement to remember: the entire error is uncertain in nature. That has to be taken care and kept as a E. So if you observe this population regression values, that is yt is equal to beta 1 plus beta 2 xt plus error of t. This is a population regression equation and this is a sample regression equation. So here we are going to estimate E of expected. I mean, we are going to estimate this y of t. Here, when a cap is being there given means in sample, it is understood that we are going to estimate that particular values. E will be written in the form of population case and expectation cap will be written in the form of sample case. So how will we generally interpret this particular coefficients is, so interpretation of coefficients of B1 and B2. B2 represents an estimate of mean change in Y responding to 1 unit of change in X. And beta 1, that is B1, is an estimate of mean Y when X is equal to 0. I will going to tell about this B2 in detail when we see an example. So that means 1 unit of change in X responding to its Y. How actually the mean change takes place, I will explain in detail in the later slides. So here I'm explaining, we will going for a simple linear regression, we will going to get beta 1 and beta 2, that is B1 and B2 in this case. So B2 means an estimate of mean change in Y responding to 1 unit of change in X, and B1 is estimation of mean Y when X is equal to 0. It must be very careful to interpret that the estimated intercept, since we usually do not have any kind of data points near X is equal to 0. So what we need to note here is regression analysis cannot be interpreted as a procedure for establishing cause and effect relationship between the variables. So here, when we do with an example, we will clearly understand what for this cause and effect generally act on it. So till now what happens is, I just explained there will be some kind of a regression which generally possess two kinds of variables. One is dependent and one is independent, and one intercept will be there that is also called as constant. So we are trying to find out some functional form on those particular explanatory and dependent variables, and understood all these things will happen under the condition that of linearity. So here the question comes, here we can directly say what is B2 and what is B1. We are saying that it's a coefficient and it's a constant, and in some textbooks it's called as slope and an intercept. But okay, how we need to estimate that particular things is, it's only with ordinary least square estimates or generalized least square estimates and or maximum likelihood estimates, or different kinds of estimation procedures are there. So for our syllabus, for our topic, we have ordinary least square estimation procedure. So we will see how actually it is. I have not entered into completely mathematical aspect of it, but some procedure to estimate these beta coefficients. See here, the least square estimation of the mean response mu naught cap, that is for the sample data, we need to estimate this particular mu naught, that is a response of this beta 1 and beta naught. So here we have to focus on the error aspect. We have to focus on the error aspect and estimating the mu naught, that is mean of this particular value and variance of that particular values. See here, if you see this particular graph, we have to understand that this particular has some kind of mean response, and here also this has some kind of mean response. So this mean is equal to this mean, so we have a constant mean. So mu naught is equal to mu1. So like that, so many things will happen. So this is a homoscedastic kind of a stuff, so that I will explain later. So mean response is mu cap and predicted y response. So these things are moving in a linear direction. So we generally estimated the linear equation. So with the constant mean, these moving in a linear direction. So instead of that particular derivation, I bought this picture, so to make you understanding in a simple way. But anyway, these are the end results of those things. So I have done some kind of mathematical algebraic equations into it. So I will explain with the help of beta 1. I mean, without beta 2, I will explain just beta 1, and later we will go to beta 2. So predicting YT without any explanatory variables, how we have to do? So we have a general form of equation. So we have that response variable at time t, that beta 1 plus e of t. So we have to do some second order differentiation, and then we have to estimate this beta 1 by minimizing it to 0. So b1 is equal to y dash. And here we need to explain this, but we need to enter later. We need to later introduce this beta 2 component into this particular equation, and then derive the same procedure again. And we will going to get this particular cap. What is this cap? Cap is an estimated figure of the entire equation. So up to here, this is one sort of equation. This is b1 plus beta b2 x3 xt, and this estimation of this particular unexplained variation component. So this is an explained variation. That means how much influence of explanatory variable on the response variable. But unexplained variation is this particular error term. This is generally yt minus y cap, that is equal to yt minus b1 minus b2 xt. So I have reduced a lot of mathematics in this, so I have not shown, but I made some kind of pictures which will generally explain to you what these things tells to you. See, this portion, the red color portion, is a aspect of this equation, that is y cap, that is b1 plus b2 plus x, and whatever the black color one is there, that is an error term. So everywhere that general thing exists. So this particular portion and this particular portion and this particular portion and this here, always these error will be there. So in this form and in this form and in this form and here also. So explaining variation in YT. So this is total sum of squares and regression sum of squares and error sum of squares. The entire equation is composition of SST is equal to SSR plus SSE. These things I mean, whatever the derived stuff, what we got in the SST, that I have kept as this one I have kept as SST, and the regression one I have kept as SSR, and then this one has kept as SSE. So this is a general established relation. If you generally observe your regression curve, you will going to have this kind of picture when you observe the any of the computer generated output of any particular software. If you see in SPSS, or if you see in Strata, or if you see in any of the thing, the linear equation generally focuses like this only. So this is total variation. I have explained this one. And this is some SSR, that is regression sum of squares. It is being explained in this form. That is fitted of y cap t values, that is yt is equal to b1 plus b2 xt. SSR measures of variation of yt around y bar. SSR is equal to this particular regression equation, which is generally termed as beta 2 of the sum of xt minus x whole square. So this is error sum of square. Error sum of square is being estimated like this, and we can call it as measures of variation of yt of this particular SSC, and the entire last product has been is sum of t goes to 1 to t of it is error of t estimation, that is cap is there here. And everyone has seen this particular table called as ANOVA table, which has some kind of source of variation, explained and unexplained. Unexplained is always called as an error. Explained is called as coefficient. And then there will be some degrees of freedom, total minus 1. Sum of squares. Sum of squares means how many things which generally contributes to total sum of squares. Mean sum of squares, that is generally sigma. Okay. After this particular ANOVA table, we will have a clear picture of the entire regression equation in the form of coefficient of determination. So what proportion of the variation in yt is explained? This is our ultimate agenda generally. The entire equation explains proportion of variation in the entire y. So the equation is range is 0 less than or equal to r square less than r square less than or equal to 1. So the r square always should lies between 0 and 1. So r square actually focuses on SSR divided by SST. So sum of regression sum of square divided by total sum of squares. So I have just given a picture how we got this particular one. So what is this total probability of 1 r square, and r square is generally this one. See, in our studies, many people are generally focuses on r square Am I audible to you?
Yes, sir. Yes, sir.
I think there is some interruption. Is this my screen is visible to you?
Yeah, okay, sir. Okay.
Yeah. I'm explaining about coefficient of determination. That is, so it's a descriptive measure for the any regression model. So the composition of R square is like this. That is SSR divided by SST. So R square is not only a.
Hello, sir.
Sir,
I think
screen is not visible, sir.
It's not visible.
Yes, sir. You have not shared the screen.
Oh my God.
Now it is visible, sir.
It's clear?
Yes, sir.
Okay, thank you. Okay, so I'm telling about the coefficient of determination. So R square, we have some results when we see the, when I receive some papers to verify. So I will generally find very high R square or very less R square, but they show some kind of significance. It's a descriptive criteria when we generally follow, but R square itself won't give you the entire picture of the quality of your regression model. There are some other criteria to follow, but R square is one of the sufficient decision criteria for the completeness of the model, but it's not an entire the quality of the model won't generally give you the by the R square. Okay, now we will see some tests. When we generally conduct the regression equation by any of the computer software, or any of this statistical tool, we will get the output in such a way that we will end up with t-test of that particular explanatory variable for the respective value, that is beta coefficient divided by its standard error. We will get a t value. The t value, whether it is significant or not, we will get that 4 aspects. Okay, here the hypothesis is that beta 2 is 0 and beta 2 is not equal to 0. So we generally conduct a small t test. I will show you how. So this is a computer output of any regression estimates. Many of them have seen it, I think so. So this is the parameter estimate. This is nothing but an intercept called as constant, and x is nothing but a coefficient. So these two we will generally observe, and the standard error also we will come to know. So when we divide this 40.7676 divided by 22.1387, it will going to give a t statistic. That is, it will give the value of this. If it is less than that of, see, it is less than 1.96. So that means the 5% level of significance criteria won't accept this particular intercept. So that 0.05 is the 5% level of significance. So this constant is okay, but when we focus on this particular variable, it seems to be significant, because when we divide this beta coefficient parameter estimate divided by the standard error, we will obtain this particular thing. Ultimately, our 1% level of significance is what? 2.58 generally. If you see the level of significance of this range, that is confidence intervals, we will get for 1% it is 2.58, for 5% it is 1.96. If that particular t-test value, test statistics value is above 1.96, we will automatically get some significant value in the probability aspect. See, this 4 is higher than this 2.58. So automatically we got significance here. So behind the screen, back end, what generally happens is B1 is estimated to that particular least square estimates. When we were actually doing our practicals was involved estimating this beta by we need to do by calculator, but it was a difficult task. But of course now systems are available very easily to get generated by B1 or B2 or up to Bn also. So what we will get these if you previously see the computer generated output, see this is a B1 and this is B2. So the same B1 value is here and B2 value is here, and the standard error of B1, that is a square root of that particular variance, we got this 22.18. This is standard error, and standard error of B2 we got 0.035, and this beta B1 divided by this standard error, we will going to get the t value, and then beta 2 divided by this t, we will get this particular value. So these two value, so we generally we use this particular beta value to explain the variations among the relations. And sources of variations in the dependent variable. See, this output is also will be get generated when you run the SPSS output or a stat output to see the R square, that is coefficient of determination, this R square. Okay. When we do manually, we have to calculate each and every stuff. But when we generally carry out in the software, we will going to get this R square by default. So this is 0.317 is an R square value, which is not that great. So here the reporting regression results is R square is 0.317, means this R square value may see low, but it is a typical in studies involving cross-sectional data analyzed at individual at micro level. So there are two kinds of aspects. One is a micro level and a macro level. So considerably higher R square would be expected in studies involving time series data at an aggregate of macro level. So higher R square will be required when we have a large series data. And when we have a cross-sectional data, then lower R square, that is 0.5 or 0.4 is also, it is acceptable only, because cross-sectional data always yields the lower level of R square. And when we have a time series data like GDP, when we are estimating, or any kind of a larger time series, we expect R square should be above 8 or 0.8 or something like that. So these are the different kinds of things which I need to explain regarding in this particular so in this particular session. So what I have done is, one is I have introduced a word called as regression. In that regression, there will be two different kinds of regressions, simple and multiple. So I have never, you may ask, I have never talked about multiple regression. So multiple regression means your explanatory variables will be more than two generally. The procedure of estimating the entire thing will be remain same. We generally apply least square, ordinary least square estimation procedure, and to estimate these betas. Okay. Now what I will going to do is, I will going to summarize this particular thing, and we have some set of questions for that particular agenda of this particular what is that this training. I have some questions and I have collected from some sources. Maybe this kind of questions may appear in the examination. Okay. So now tell me, will be from your side, the number of explanatory variables in the simple linear regression will be? Hello?
1, sir.
Okay, fine. So the same question can be asked in different form. They will give one equation. If it is multiple linear equation, y is equal to a plus x1 plus x2, x3, x4 plus error. And in that point of time, they will ask how many explanatory variables exist. Okay. At that point of time, you have to see the value of x. Is this clear? And can you answer the second question?
First option, sir.
What is the range of this particular R square? A, B, C, D.
Yes, sir.
A.
A.
So it's always lies between 0 and 1. Of course, all the options are looks like this, but 0 less than or equal to. Okay, A. Fine. When you go for the third one, what will be
D.
the answer for the third one?
C.
C.
B, sir.
Yeah. If you want to see means anyway, my slides will be sharing to you. You can have RSS divided by TSS. And what will be the answer for the fourth one?
First option, sir.
Y is a regression, X is an explanatory variable, isn't it?
Ha, sir.
And the third one, I mean fifth one. Can you tell the answer for the fifth one? Hello? Yes, tell me. 5:30. No. See, it is been estimated through ordinary least square estimation procedure when we go for a simple linear regression. And can you explain this, the last, that is sixth one? Given a coefficient b is equal to 2 and a standard error is equal to 0.5, the value of t ratio is? Anyone? See here, this question can be answered in a simple way. So the formula for T ratio will be beta 1 divided by, B divided by SE. So that's 2 divided by 0.5, how much we will going to get?
4.
So
4.
B will be the answer. So they will going to change the values, but question remains same. So B will be the answer for sixth question. And I have few more questions to tell. Last, okay. So, okay. The seventh question is in statistics, the reliability of an estimate is measured by. The reliability of an estimate is measured by. So you remember very clearly, reliability. In anyone? See, the reliability of an estimate means here we need to understand the other options. See, student t value, it will calculate some test. F is also, it will calculate some test. P value will going to give you some level of significance range, and standard error means it will only tell you how much error generally present in this particular setup. So lower the standard error, higher the reliability of a particular estimate. So always we need, when a validation or reliability asks relating to any kind of estimate, estimate means beta coefficient estimate, we generally focus on standard error itself. If you see the regression output only, we will come to know the standard error. And then can you anyone ask this, answer the 8th question? B. Okay. The next. See here the ratio of total sum of squares and explained by sum of squares means it is simply R square, coefficient of determination. So here they have given coefficient of correlation, coefficient of variation. Again, they have given coefficient of variation itself. So coefficient of correlation means it is R value only R. Coefficient of determination means R square. Coefficient of variation means CV, and this is also CV. The range of this correlation is 0 -1 to +1, and this range is 0 to 1. This kind of question may also ask. Okay, a linear function has varying slope and constant elasticity. I mean, can you answer this particular 9th question?
4th option, sir.
Okay. Yeah, correct. And the last one. What is the full form of that CLRM?
A linear regression model ಅಂತ ಬರುತ್ತಲ್ಲ sir.
ಹೌದು. So it means that classical linear regression model. So generally in some question papers I have seen like this classical linear regression model. Simple, they will ask only what is CLRM. Okay, it's a standard one. Now answer this question. One of the assumptions of classical linear regression model is that number of observations in the sample must be greater than that of
C, sir. Option C.
option C. Actually, the option is A, regressor. See, here number of observations in the sample should not cross the regressor means, see here you have to understand the meaning of this regressor. Regressor means independent variables, regressors. Okay, and regressor, I mean they will just confuse you. If they have given only independent variable, that might be the answer also. Regressor, regressants means this is dependent and this is independent. So these 10 questions I have, and I have further other questions also. If you want, means I can other send. So this from MLR topic means this kind of questions may generally appear in the examinations. Now tell me if you have any kind of queries, I will happily answer to you. So last 10 minutes is there. This is for generally asking questions because people are preparing for the higher examinations and you have lot many questions.
Yeah, thank you, sir. I request all the participants, if someone has any queries or doubt regarding this session, please ask to sir. We know that it is little bit mathematical portion and it is very difficult to explain in this PPT form, but sir did his best. But if someone has any queries or doubt, so please ask to sir.
You can put it in the chat box also if you have any specific queries. If there is no queries, means the next session will going to start at 4:30. Praveen sir. Hello, Mr. Praveen.
Yes, sir.
So shall we start the next session at 4:30?
Yeah, okay, sir. We will take 5-minute break and then we will start, sir.
Yeah, thank you.
Okay, sir. 4:30 we will start.
Yeah,
Okay,
thank you.
Hello, sir.
Yes, tell me.
Sir, statistics related to idu first lecture, sir.
Yes, yes. Sir, actually, we are not taking separate lecture for statistics, sir. According to syllabus, we will take sessions, sir. Generally, it include in econometric sessions. So we are not taking separate lecture for statistics.
Okay, sir. But in the timetable provided before, na sir, but
Okay.
the statistics related syllabus are from 24th.
Yeah.
These topics may
No.
cover in econometric part also, specifically. Statistics
Yeah,
means,
yes,
I
sir,
mean,
yes, sir.
I have been assigned some, it's both. When we linear models will come in statistics as well as in econometrics also.
Sir.
I think they have given to me only these topics. Thinking that it's belonging to econometrics, I think statistics may have a next sessions, I think so.
Sir, ನಾನು ಸ್ಟಾಟಿಸ್ಟಿಕ್ಸ್ ಓದ್ತಾ ಇದ್ದೀನಿ ಸರ್ ಈಗ MSc.
ಸ್ಟಾಟಿಸ್ಟಿಕ್ಸ್ ಇದು ಅಗ್ರಿಕಲ್ಚರ್ ಎಕನಾಮಿಕ್ಸ್ ಸ್ಟೂಡೆಂಟ್ಸ್ ಅಂತ ಹೇಳಿದ್ದಾರೆ.
ಸರ್, ಇದರಲ್ಲಿ ಸ್ವಲ್ಪ ಟಾಪಿಕ್ಸ್ ನಮಗೆ ARS ಮತ್ತೆ SRF ಗೆ ಬೇಕಾಗುತ್ತೆ. ಅದಕ್ಕೋಸ್ಕರ ಕೇಳ್ತಾ ಇದ್ದೀನಿ ಕ್ಲಾಸು. ಇದು ಫಸ್ಟ್ ಕ್ಲಾಸ್ ಸರ್ ನಂದು. ಆಕ್ಚುಲಿ 24th ಇಂದ ಆಕ್ಚುಲಿ ಟೈಮ್ ಟೇಬಲ್ ಅಲ್ಲಿ ಇತ್ತು. ನಾನು ಇವತ್ತು ಸುಮ್ನೆ ನೋಡೋಣ ಅಂತ ಬಂದೆ ಸರ್. ಅದು ನಿಮ್ದು ಕ್ಲಾಸ್ ಇತ್ತಲ್ಲ, ಅದು ಹೆಡ್ಡಿಂಗ್ ಅಲ್ಲಿ ರಾಯಚೂರು ನೋಡಿ ಕೇಳಿದೆ ಫುಲ್ ಕ್ಲಾಸ್. ಸರ್.
ಆಯ್ತು, ಅದು ಆಸ್ ಪರ್ ದಿ ಟೈಮ್ ಕೊಟ್ಟಿದ್ದ ಟಾಪಿಕ್ ಇದು ನನಗೆ, ಅಂದ್ರೆ ಎಕನಾಮೆಟ್ರಿಕ್ಸ್ ಅಂತ ಅನ್ಕೊಂಡು ಕೊಟ್ಟಿರ್ಬೋದು.
ಸರ್.
ಬಟ್ ಐ ಡೋಂಟ್ ನೋ, ಐ ಹ್ಯಾವ್ ನಾಟ್ ಸೀನ್ ದಿ ಫುಲ್ ಶೆಡ್ಯೂಲ್.
ಓಕೆ ಸರ್.
ಆಯ್ತು. ಇನ್ನು ನಿಮ್ಗೆ ಎಕ್ಸ್ಟ್ರಾ ಏನಾದ್ರು ಬೇಕಂದ್ರೆ ನಂಗೆ ಮೇಲ್ ಮಾಡಿ, ಆಮೇಲೆ ನೋಡೋಣ.
ಓಕೆ ಸರ್, ಥ್ಯಾಂಕ್ ಯು. ಸರ್ ನಿಮ್ಮ ಮೇಲ್ ಐಡಿ ಏನಾದ್ರು ಕೊಡ್ತೀರಾ ಸರ್?
ಕೊಡ್ತೀನಿ. ಲಾಸ್ಟ್ ನೆಕ್ಸ್ಟ್ ಸ್ಲೈಡ್ ಲಾಸ್ಟ್ಗೆ ಹಾಕಿರ್ತೀನಿ, ಅದು ತಗೊಂಡು.
ಓಕೆ ಸರ್, ಆಯ್ತು.
ಓಕೆ. Shall we start the session, Praveen?
Yes, sir. Yes, sir.
Okay. So welcome to my second session. So that is generally when we talk about linear models, the continuation of that linear models is these aspects.
Yes, sir. Yes, sir.
Okay. So all are there? Yeah. So the topic given to me is properties of estimation in multicollinearity, heteroscedasticity, and autocorrelation. So these are generally seen in linear models. If we see the econometrics aspect, these things are very, very important to finalize or to validate the right model for econometric econometric part. So here the first thing is estimation. Estimation procedure, that is in that estimation procedure, in the sense on ordinary least square estimation procedure we have seen in the previous thing, and when we come over here we have to understand the properties of estimators, that is estimation. We have 4 properties of estimation, that is unbiasedness, consistency, efficiency, and sufficiency. We will discuss one by one. So estimation procedure is very, very important. If we follow all these, if it is only satisfies all these kind of properties, generally the process of obtaining an estimate of an unknown value of the parameter by a statistic is termed as an estimation. So we have a point estimation and an interval estimation. So these things generally focus on point estimation. So the first one is unbiasedness. Bias means there is some difference exist. Unbiased means there is no difference exist as per the general meaning. So an unbiased estimator of a population parameter is an estimator whose expected value is equal to that of the parameter. Formally, an estimator mu cap for the parameter mu is said to be an unbiased if it is expectation of mu cap is equal to mu. So sample means an unbiased estimator of population mean. So like that we generally see, or expectation of theta cap is equal to theta. So the concept of unbiasedness is one of that of concern with relationship between the true value of the parameter and the mean of all possible values of an estimator. So it is important to realize that other estimators for a population mean exist. That is mean value in a sample, minimum value in a sample, maximum value in a sample and minimum value in a sample, average of the maximum and minimum value in the samples. Being unbiased is a minimal requirement for the estimator. For example, the maximum value in the sample is not an unbiased and hence should not be used as an estimator for mu. So it is very simple to understand. Whatever the expected value of that particular parameter is equal to the original value, then it is seems to be an unbiased estimator. So generally this particular equation is only holds good for unbiasedness. So next thing is consistency. An unbiased estimator is said to be consistent if the difference between the estimator and the target population becomes smaller. And as we increase the sample size, formally an unbiased estimator mu dash, that is mu cap for a parameter mu, is said to be consistent if the variance of mu cap approaches 0 as n tends to infinity. This is one of the rule for the consistency. So the concept of consistency is concerned with the variability of an estimator. If the value of an estimator theta cap or mu cap approaches to the parameter theta more and more closely, as the sample size is increased, then theta cap is said to be a consistent estimator of theta. An estimator may be unbiased or consistent or both. Still, it may not be the best estimator. it will be the best if in addition unbiasedness and consistency is an efficient estimator. So the next thing is called as an efficiency. So what we are talking is, we are talking the properties of an estimators. So the third one is called as an efficiency. In comparison of various statistical procedures, efficiency is a measure of quality of an estimator, of an experimental design or a hypothesis or any of the testing procedure. The measure of the efficiency is the ratio of theoretically minimal variance to the actual variance of the estimator, which falls between 0 and 1. An estimator with efficiency 1 is said to be the efficient estimator, and efficiency of the given estimator depends on the population. See, in the questions, how they will ask is, if the efficiency of this particular value is 0.8, then what will be the efficiency, like that 0 and 1 range kind of thing will be there, means then they will ask the questions based on that range. So the estimator with the smaller variance will deviate less from the true value of the parameter than the estimator with the larger variance. See, in other words, I mean to tell you, the smaller the standard error, the greater the precision of the estimator. Hence, the efficient estimator is one whose variance is very, very small. So this is about the efficiency. And it's the last property is sufficiency. A statistic is sufficient with respect to a statistical model, and it is associated with unknown parameter if no other statistics can be calculated from the same sample, provides any additional information as to the value of the parameter. See, sufficiency concept is somewhat intuitive. That is, if the estimator utilizes all the information relevant to the parameter that is available in the sample, then the estimate is said to be sufficient estimator of the parameter. I mean to say, in other words, an estimator is said to be sufficient if no other estimator can be computed from the sample. So these are the 4 properties which generally comes in the form of properties of an estimator. So unbiased estimator means it will be result like this. The result is this one. We have a cap here, and the beta means the distribution of beta is centered to beta 2. Since the distribution of beta B2 is centered to beta 2, we say that B2 is an unbiased estimator of beta 2. And then consistency, we'd like our estimators B1 and B2 to collapse onto the true population B1, beta 1 and beta 2 as a sample size t equals to infinity. So on the way to achieve this consistency property for the variance of B1 and B2 to go to the 0 as t goes to infinity, since the formulas for the variances of at least square estimators B1 and B2 shows their variances do. In fact, it may go to 0, or then B1 and B2 are consistent estimators of B1 and B2. So all these kind of assumptions of a simple linear regression model, the ordinary least square estimators B1 and B2 have a smallest variance of all linear and unbiased estimator of B1, beta 1 and beta 2. This means that B1 and B2 are the best linear unbiased estimator, called as blue, of B1 and B2. See, when we go deep into the statistics, we have a theorem called as Gauss-Markov theorem. If students who particularly focus on statistics, we have learned this Gauss-Markov theorem, which gives the properties of one of the estimators, that is blue. Generally, they will ask the questions like, what is a blue? Blue means the best linear unbiased estimators, which is generally focused on the smallest variance of all linear and unbiased estimators. Then it will be called as a blue. So these are the properties of estimation. So the next thing we are going to is meaning of autocorrelation. See, these are the criteria to fill to be a good model. So I will tell one by one. There are 3 things. One is autocorrelation, one is multicollinearity, one is heteroscedasticity. Separately, I will tell the meaning of each one, and then what is its consequences and how it can be addressed to be a good model, and how it can be detected. So meaning of an autocorrelation. Autocorrelation is also called as a serial correlation. occurs when error follows a pattern. It reflects the violation of a linear regression model assumption that error terms are not related. That is, autocorrelation is a common problem in the time series regressions. It indicates that some relevant variables are not included as an explanatory variables. That is, explanatory means, as I said, it's a independent variables in the model. So the word autocorrelation and serial correlation are used synonymously. However, the autocorrelation means lag correlation of a given error term with itself. The serial correlation is a lag correlation between two different series of error terms. See, if these problems generally, if you see, if people are working in econometrics, if you run any kind of distributed lag models or autoregressive distributed lag models, you will occur different kinds of problems in autocorrelation or multicollinearity or heteroscedasticity. When we talk about the regressive models, that is distributed lag models or something like that, we have a problem of lag, that is by the value actually depended on by itself. At that point of time, the serial correlation is the lag correlation between the two different series of error terms. So then this problem generally seen invariably. So autocorrelation can be the first order or higher order. The first order autocorrelation is presented in the model if an error is influenced by the error from preceding time period. See, as I said, the lag means its previous value. The models generally focuses on autoregressive kind of stuff. That means yt is equal to t minus 1. That is, yt is an response variable and yt minus 1 is an explanatory variable. When this kind of setup or this kind of linearity functions or establishment happens, then this autocorrelation automatically will influence their errors. See, the first order autocorrelation is presented in the model if an error is influenced by error from the preceding time period. Autocorrelation can be positive or it can be negative. Positive autocorrelation occurs when the error tends to keep same sign for one period to the next. So positive autocorrelation occurs when the error tends to keep the same sign from one period to the next. Negative autocorrelation occurs when the sign of the error terms tends to change its sign regularly. So this positive autocorrelation and negative correlations has has its impact. See, this is when we draw some kind of graphs, it will be seen like this. So, okay, what autocorrelation exists, what we actually need to do. Even when the residuals are serially correlated, the presence of autocorrelation in the model, the estimated OLS parameters are unbiased and consistent, but they are not efficient. So the presence of autocorrelation affects the standard error of the estimated parameter. Hence, the estimated parameters have smaller standard errors, consequently narrower confidence intervals. So if we see generally the previous slides, it is some kind of connectivity. See what here the consequences we may face is the presence of autocorrelation affects the standard error of an estimated parameters. Hence, the estimated parameters will have a smaller standard errors, consequently narrower the confidence intervals, which will lead to some kind of problem in the entire model. I mean, validation of that model. I mean, the quality of the model which we generally build. So what happens if that's so? Therefore, the usual F test will no longer be valid and lead to the misleading inference and prediction. This is what generally happens if we have a high autocorrelation. Those who generally work in autoregressive distributed lag models in econometrics will definitely have experienced this kind of phenomenon, because I also worked in this when one of my paper was autoregressive distributed lag models. I have generally faced this problem of autocorrelation. when I clearly seeing the p values of t and f. Of course, they are significant, but they are generally misleading to frame a inference or prediction. So in this case, what happens? R square and f statistics may be overestimated. R t statistics are overestimated. As I said, right? R square will be 1. R square will be 0.99. Or R square will be 0.0. Or this kind of R squares we generally observe if we have a high autocorrelation. So the regression also includes that a lag dependent variable, then OLS estimates will be biased, besides they are inefficient. So how we need to detect the autocorrelation? Okay, autocorrelation means these are the consequences which we have understood. And how to detect this one? If we plot residuals against time, then it shows that systematic pattern, then autocorrelation is present in the model that we generally know. That means what I'm saying, if we plot the residuals, that is the error terms, against the time, and it shows systematic pattern. The parallelogram is there. If we use some, this is one of the tool to see the residual covariances or variances. It will confirm no autocorrelation in the residuals if the autocorrelation and partial autocorrelation for all the lags will normally 0, and the Q statistics are insignificant with large p values. Generally, if you plot the residuals against the time, it will not show systematic pattern. See, this is a output which I have taken from EViews. If you observe autocorrelation, see, this is autocorrelation and this is a partial correlation. See, these are the values for autocorrelation. So what we can do is, this is one is detection. This means when we see the parallelogram, we can identify that there exists some autocorrelation. And the second one is the Darwin-Watson test, which is given by Darwin and Watson. What is this test means? The test provides the test for the first order autocorrelation, most common autocorrelation it is. I mean, generally, if we see the value of this particular test, the condition for this DW test is the regression model, which includes an intercept term, and there is no lag dependent variable in the model. What we do is, if the DW is 2, then there is no autocorrelation. If 0 is less than DW is less than 2, then there is some degree of positive autocorrelation. In the worst case, it will be near 0. If 2 is less than DW and 4, there is some negative autocorrelation. So our DW statistics, that is DWT, will give you a very simple way of whether the autocorrelation is present or not. If DW is 2, then there is no autocorrelation. If it is exceeded 2, then there is some autocorrelation exists. If there is a lag dependent variable in the regression model, then DW test is no longer valid. So this is another problem for DW test. What is this problem means? I said, right, if there is a lag dependent variable, lag dependent means the value, the series is dependent upon its lag value, then DW test is no longer valid. In this situation, we generally use LM test. So this is Lagrange's multiplier test we generally call. The null hypothesis of LM test is there is no autocorrelation. If the value of F test is small and its probability value is more than 0.05, then in that case we accept that there is no problem of autocorrelation in the model. When we have to use this one, if the DW statistics test statistics is not at all giving a valid result, I mean, in that case of lag dependent variable, we have to use this LM test. in the questions of the in the net or something like that, this they will going to give d value is 4, then what is your conclusion? Or LM test is above the significance, what will be your conclusion? This kind of questions may generally appear. Or what are the find the following tests for the detection of autocorrelation? This kind of questions may appear in the examination. So remedial measures of autocorrelation, what we generally do is different approaches are used to treat the autocorrelation. The best approach is to reformulate the regression model and re-estimate the regression coefficient to eliminate the problem of autocorrelation. So many times we actually have to add or removing the variables to change its functional form. Then it will reduce. And however, in some cases, the autocorrelation problems cannot be removed completely, but we generally minimize it. See, we have some Cochran's Orcott methods of AR1, autoregressive element 1, a method to eliminate the autocorrelation problem. So those who have used ARIMA autoregressive distributed, autoregressive integrated moving average model, their autoregressive term is there. That is one of the forecasting methodology. It has used one autoregressive term. Autoregressive means yt is dependent upon yt minus 1. That means what? A dependent variable of time t is dependent upon its previous value. That is t minus 1 means time minus 1. So this is about a general autocorrelation. You have understood what is autocorrelation, what is the meaning of autocorrelation, what happens if autocorrelation present in the model, and how we need to detect that. To detect that, we can use the correlogram in the softwares which will generate, or we can use we can see the DM test, or we can see the LM test. Next, we need to understand the meaning of multicollinearity. Multicollinearity is a linear relationship among some or all explanatory variables of the regression model. So the multicollinearity can be perfect or imperfect. If some explanatory variable is some multiple of other explanatory variables, the multicollinearity will be perfect. See this statement, I will read it again. Multicollinearity can be perfect or imperfect. If one explanatory variable is some multiple of other explanatory variables, the multicollinearity will be perfect. In the case of perfect multicollinearity, we cannot find the estimation of regression model. When we generally run the models in the econometrics, we will generally appear the singular matrix, because the matrix is multiplied with matrix, we will get that error. That is when we generally see if you have one variable called as 2, 4, 6, 8, and it has a multiple of 4, 8, 10, that is multiple of other explanatory variables, then it's a perfect multicollinearity problem. It is collinearing with multiple times with that particular variable. So those two variables generally won't use any kind of predictability in the regression model. Multicollinearity does not reduce the model of the predictive power, it only affects the coefficient of independent variables. So what are the consequences generally? This is the meaning of multicollinearity. Multicollinearity consequences we will generally see now. So larger variance and standard errors of OLS estimators. So insignificant T ratios of OLS estimators leading to the acceptance of null hypothesis that the true population parameter is 0. So if we generally see the consequence, this is one of the important one. We will have a large variance in standard errors. When we have a larger variance, automatically our model doesn't have any kind of significance. If you have a higher standard error, it doesn't have a reliability. Reliability of that particular estimator will not be there if you have a higher standard errors. And insignificant T ratios of OLS estimator leading to the acceptance of null hypothesis, that is the true population parameter is 0. So when we got generally T ratios is insignificant, then automatically those things will not be taken care into the the predictability of the model. The high adjusted R square, but a few coefficients of the regression models are significant. So this kind of problems, when we run the data multiple times, we will come to know. So unstable OLS estimator, a wrong sign of pure regression coefficient. So whatever the beta coefficients we have, we will going to get a very high values. That is, we will going to get the values in in lakhs or crores, or it is very minimalistic 0.000 to the power of 17 or something like that. We will get those values. We will not going to give any kind of predictability with our explanatory variables to the response variables. Then this will become a big problem in understanding what actually it contributes to the responses. So the OLS estimators and the standard errors become sensitive in small changes in the data, and OLS estimators are still linear, unbiased, and normally distributed, but they are not efficient. So these are the consequences we generally feel when the multicollinearity exists in the data. So how to detect this multicollinearity? High pairwise correlations among the explanatory variables. Okay, it is a very fundamental one. If there is a high correlation, so it is understood that there is a multicollinearity. A prior knowledge of the relationship among the variables. High adjusted R squares, the coefficients are significant, and the coefficient of models are statistically insignificant, but overall the F model is statistically significant. So what we will going to get is, if we see the T stats, it will be significant, but F will be significant. So this kind of things, we will understood that there exists a multicollinearity. And by seeing the data itself, we can generally see if we have a high pairwise correlations, or if we generally run the data of correlations among the explanatory variables, we come to know that there exists a multicollinearity. And what are the remedial measures of this multicollinearity? We need to see. Increase the size of the sample, one thing we can do, and drop variables from a model. That means when we frame the model for our data set, adding or dropping the variables from the model, or a dummy variable can be added or it can be deleted. Something can be done to avoid the multicollinearity problem. So or transformations can be done by doing its log linear into the variables, or what we can check is the first difference form. See, we have some criteria like ICAR information criteria, or BIC, EIC, and VIC. Based on that criteria, we generally see the result. Before that one, it has to pass the test, ADF test or PP test. Those things, I mean, the stationarity of that particular test. If we do the first difference, or second difference. So find out which independent variables is some combination of other variables of the model, and or remove it. So what we can do is we have to see the independent variables very clearly, and we have to redesign the independent variables in such a way that there should not be any kind of high correlation problem exist in the independent variables. Then those things can be avoided. So what we can do is combine the cross-sectional and time series data that can be pooled in panel data for analysis. So when we do the research, we will come to know which variable is generally can be removed, or which can be added, and that can act as a some catalyst that can remove the multicollinearity. So these are the remedial measures that generally we can follow to reduce the multicollinearity. So the next thing is called as heteroscedasticity. So what we have learned till now is properties of estimation. So that is unbiasedness, consistency, efficiency, and sufficiency. Those are the requirements for be a good estimators. And then afterwards, for continuing the right validation of model, we have some problems of autocorrelation or serial correlation. And the next thing is multicollinearity. And the next important thing called as heteroscedasticity. That means an essential assumption of the linear regression analysis is that error variance is constant. Homoscedastic. Homoscedastic means variance is constant. If the variance is not at all a constant, then the problem of heteroscedastic arises. If the error term variance is not constant, then there is a heteroscedasticity problem exists. This means error terms observations are coming from more than one probability distribution. So heteroscedasticity mostly occurs in regression models that are based on cross-section data. So where there are differences in the heterogeneity in the observations. So heteroscedasticity mostly occurs in regression models means if we generally see the cross-sectional data or panel data, there exists heteroscedasticity. If we observe the data patterns, we come to see. I mean, the underlying probability distributions are not same generally at that point of time. So this is a representation of the heteroscedasticity problem. Homoscedastic and heteroscedastic. And these are now what we have to see is if the heteroscedasticity presents in the data set, then what actually the consequences we have to face. The OLS estimators are still unbiased, but they are no longer efficient. The causes that the OLS procedure to underestimate the standard errors of the coefficients, the t statistics are larger than they should be. The f statistics will also be larger than the true value because the t statistics and f statistics are larger than the actual. The null hypothesis should not be rejected. See, if actually someone worked on this particular kind of panel data or cross-sectional data, they will generally have experienced this heteroscedasticity problem. If you observe the results very carefully, we have a high t statistics values or high f statistics values in the results we generally see. Then what happens is we try to do that. The null hypothesis should not be rejected. We have to accept the null hypothesis that these things exist. So we have some kind of tests here to detect the heteroscedasticity. The most famous white heteroscedasticity test. If the probability value of f statistics or a chi-square test under the white heteroscedasticity test is more than 0.05, we accept that null hypothesis that the residuals are homoscedastic. So if it is less than 0.05, we tell that there is heteroscedasticity. The autoregressive conditional heteroscedasticity ARC LM test is also used for it. If the probability value of f statistics or chi-square statistics is more than 0.05, we accept the null test that residuals are homoscedastic. See, these are the two tests which we generally identify to, use it to identify this heteroscedasticity. And the null hypotheses are like this, and then we do the respective action about that. So here the detection of heteroscedasticity is if we plot the error term observations and see the systematic pattern, this shows that heteroscedasticity problem. See, majority of the data sets, if we plot along with the data set, we will observe different kinds of things in that particular aspect. Many of the problems will be seen or solved when we generally do some kind of graphical analysis. This particular one, what I'm talking about is if we have to plot the error terms. Here, error terms can be plotted if someone has used the eView software. The error terms will be generated, and if you plot that one, then we can see the systematic patterns. If heteroscedasticity present, there won't be any systematic pattern. The nature of the data gives information about the heteroscedasticity. If we are using cross-sectional data that involves heterogeneous units, heteroscedasticity may be present in the regression results. So what we can do is, when we have a heteroscedasticity, we have to do some kind of transformation. A log transformation is a very appreciable thing, which generally I suggest for heteroscedastic problem, and then estimate the model for subsamples with homogeneous group. What I generally do, if the data is very big, we can do the subsample estimation procedure, but if the data is small, we cannot go for the estimation of a subsample procedure. But it is one of the recommended measures to remove the heteroscedasticity. Estimate the model for subsamples with a homogeneous group. And we can use the weighted least square method if the value of sigma square is known to you. That is, if the variance is known to you, we can use the least square estimation. If the sigma is not known, the weighted least square method obtain the estimate for sigma. Then only we have to use this weighted least square. I mean, if sigma is not known, then estimation of sigma variance is another procedure to follow. Later on, we can use WLS square. So this is about the heteroscedasticity remedial measures. This is an additional information which I want to give you. When people are preparing the models, one of the classical linear regression model assumptions is that regression model used in the analysis is correctly specified. We have a problem with the model misspecification. If the model is not correctly specified, there are several types of specification errors. Generally, people will come to me with different kinds of framing of models in the economics, omitting different kinds of variables they have, but they have specified the model in a different form. When we change or interchange some kind of variables, then the model will become strong, and then the predictability capacity of that model increases automatically. Omitting a relevant variable from a model, we need to see the variable bias. Either we need to add the variable which are very much relevant, or we need to add which are not contributing to the existing responses. And then functional form is one thing which generally people do some mistakes. Functional form means the actual relationship between these responses and explanatory variables, not completely framed in a different aspect. That has to be done the way it has to be. And using the proxy variables instead of a true variables. Proxy variables which will somehow generally helps in some cases, but many cases proxy variable won't use the true picture when we do the model specifications. Apart from this thing, the forecast stability of the model, which we generally do, the regression model is often used for forecasting. After estimation of the coefficients, that is not the end of the story. If we go further, forecasting is also one of the component in the autoregressive model kind of stuff when we frame the econometrics model. Forecasting is just a way to use the variable historical data to make us the best guess about the dependent variable future. See, if we can use the GDP, or we can use any of that particular econometric models, or human development index models, as World Bank uses. If you see their beta coefficients, they use always the predictive forecast ability of the particular model which they generally built. The forecast can be in simple or out of the sample. If the dependent variables forecast is based on the independent variables, it is called as in sample forecast, and if it is outside that, out sample forecast. So you all know this is root mean square is root mean square, or RMSE is a scale dependent measure used to compare the forecast methods. And the question will be asked, what is our RMSE? RMSE is a root mean square, is a scale dependent measure used to compare the forecast methods applied to a single time series or two time series with the same unit. It is it is very easy to understand, and it can be computed easily also. And the next one is mean absolute percentage error. MAP, the mean absolute percentage is a unit free thing. Generally, we use the percentage value thing to compare the forecast performances of data sets. So apart from these two, we have something called as Thales inequality coefficients to calculate the forecast ability. What is this Thales inequality coefficient? Provides a measure how will time series estimated values compare to the corresponding time series of observed values. So the closer the value of the coefficient to 0, the better the forecasting ability of the model. So this will be one question for many a times I have seen in the papers. The value for 1 means the forecast is just to, it will not give a right picture. And the values of this Thales coefficient inequality should be very near to 0. So last thing is called as a dummy variable. A dummy variable or an indicator variable that represents a categorical data such as gender, race, affiliation, etc. Technically, what generally happens means dummy variables are dichotomous in nature, quantity variables. Their range of values is very small. They can take on 2 quantitative values. As a particular matter, regression results are easiest to interpret when dummy variables are limited. So many a times when we use simultaneous equations in the econometric form, we use these dummy variables. Dummy variables are limited to 2 specific values, 1 or 0. Typically, 1 represents the presence of qualitative attribute, or 0 represents the absence. So the question may be asked as if they will give one categorical data, whether this is a dummy variable or not. That particular quality attribute exists or not. This kind of things generally we can see in this. This can be taken as a dummy variable. See, many a times when we talk about the autocorrelation or multicollinearity or heteroscedasticity, removing or adding of dummy variables makes some changes in the model specifications. Okay. Yeah, I have some few questions here. I will explain these things and you can also answer this. See, I have almost, what I have done is I have minimized the mathematical part and I have included only theoretical setup here, because if I use more and more mathematics to represent the multi-correlation, if I use some mathematical terms, it will become a little bit confusing to people. So I have very few questions here. We will answer these questions and then we will end up the session. So variation inflation factor, that is VIF, is used for detecting multicollinearity. See, if we run the EVs thing, variation inflation factor we generally observe when we see the multicollinearity aspect. It is one of the aspect. And detecting heteroscedasticity, we can use the what kind of a test. So this kind of questions they may ask. Okay, detecting the autocorrelation, what kind of a test is being used, or detecting heteroscedasticity, what kind of a test is being used. See, if the value of the Durbin-Watson statistics is 0, then there is what is the meaning of that? Anybody? So we have a range of if it is less than 2, then we don't have an autocorrelation. If it is equal to 2, it's we don't have an autocorrelation. If it is less equal to 0, ಹೇಳಿ ಲಾಕ್ ಇದೆನಾ? ಹೌದಾ? ಹಂಗಂದ್ರೆ ಒಂದು ಕೆಲಸ ಮಾಡಿ, ಬೇರೆ ಯಾವ್ದಾದ್ರು ಕ್ಲಾಸ್ ರೂಮು, ಬೇರೆ ಎಲ್ಲ ಕ್ಲಾಸ್ ರೂಮು ಅಲ್ಲಿ ಹೇಳಿದ್ರೆ ನಾನು ಬರ್ತೀನಿ. ಇನ್ನೊಂದು 10 ನಿಮಿಷ. Yeah, tell me now. So regarding this will be a Durbin-Watson statistics. They will give certain value within the range. We need to identify whether the autocorrelation is present or not. Expectation of ui comma uj is equal to 0 when I is termed as a no autocorrelation kind of thing. It is if it is not equal to 0, then there is autocorrelation present. If there exists a high multicollinearity, then the regression coefficients are determinate. Are indeterminate or infinite values or small values, we need to tell. So the regression coefficient estimated in the presence of autocorrelation sample data is an efficient estimators. So next thing is blue. Blue is a best linear unbiased estimators. Homoscedasticity means what? Can anyone answer this question?
Minimum variance.
Homoscedasticity means constant variance.
Constant.
There is no change in the variance. Who introduced the regression?
Galton.
Okay, the 9th one. Which of these is not a symptom of multicollinearity in the regression model? See, here I need to explain about VIF. VIF is nothing but a variation inflation factor. If the VIF is less than 10, it is understood that there is no high multicollinearity exist. So all above 3, there it shows that there exists a multicollinearity. VIF, it shows that value we will going to get in the, if we run, or if we can calculate manual also, but it's a very tedious procedure to do such stuff. If the value of that particular VIF is less than 10, then it is understood that it's a good data. If it is more than 10, automatically there exists a multicollinearity data. Okay, these are the questions which generally appears in the examinations like this. So I have minimalistic mathematics in this, no mathematics at all. Actually, I have just used the meaning of that particular term by referring various textbooks. So this is the thing. If you have any questions, it's open for discussion. And someone actually asked the what is that? The email ID. I'm going to type here. So if you have any queries, it's open for discussion.
Yeah,
Or
yes, sir. I request all the participants, if someone has any query regarding this session, please ask. Because we know that, sir, it is more important topic related to generally for ICAR NET exam, sir. And for those preparing for JRF, means for PG entrance exam, those participants, it might be look like little bit confusing because it is more related to econometrics part. So I request to all the participants, if someone has any queries or doubt regarding this session, please ask.
you can mail me or you can ask directly.
Yeah.
Now only my mail ID is being given there. So we'll maximize it. If it is nothing is there to ask, I will just thank you everyone. And thanks for the organizers for inviting me for this session. Thank you.
Thank you so much, sir. We know that in a short period of time, such a huge portion is covered. It is very difficult to explain. Thank you so much for you. And definitely, sir, this session will help to our participant for their examination. Thank you so
Thank
much.
you.
And also,
Thank
I
you.
would like to thank for participant also for their patience. And
Okay, thank you.
before concluding this session, I would like to request all participants, please join morning 10:30 with our expert, Dr. Kavita ma'am. Thank you so much for all of you. Thank you, sir.
Thank you.
Thank you, sir.